Okay, today we're going to look at the Darboux Criterion. So last time we looked at a lemma, which I'll just put down here. So from last time, we had a lemma that said if P and P prime are two different partitions of the same interval AB, then the lower sum with respect to P is always going to be less than or equal to the upper sum with respect to P prime. So essentially, it doesn't matter if we choose, it doesn't matter what partition we use, upper sums cannot be smaller than lower sums, which is, it's not very intuitive, but it's a very nice result. So with this in mind, we can sort of define two objects. So what we're going to define is called the upper and lower integrals. So this is going to be the, actually I don't know which one of these, this is, yeah. So this is going to be the upper integral, sorry. And so what this is going to be is the infimum of the set consisting of upper sums with respect to a partition. So P is a partition of AB. So we look at the set of all upper sums for our function f, and we choose, well, not necessarily choose, but we pick an infimum, right? And so why do we pick an infimum, right? Because the upper sums are going to be like the bigger sums, right? So why are we picking the sort of like a small upper sum? Well, it's just sort of to say that, I guess, for one, right? So what we're going to be studying is an alternate definition to Riemann integrability, right? So we know our function has to be bounded, right? So let's say if we had something which is unbounded, right? Then the upper sums I could make bigger and bigger and bigger, but that's not really telling me any information. I want to see how low I can get my upper sums to be, because my upper sums are an upper bound, but I want the smallest, in a sense. Yeah, the smallest of these upper sums. Similarly, we're going to define the lower integral as the supremum of the lower sums, right? Where again, P is a partition. And so by our lemma, since L of Fp is always less than or equal to U of Fp prime, right? This is saying that every element in this set is less than or equal to every element in this set. And so there is a result, I think we have proved this earlier, that this essentially implies that the lower integral of f is then less than or equal to the upper integral. Again, one way you can sort of argue this is through contradiction. If you assume that the upper integral is less than the lower integral, then you can find some contradiction using properties of supremum and infimum. Okay, so with those definitions, we are going to get into the theorem. which is the Darboux Criterion, which says that a function f is Riemann integrable if and only if for every epsilon greater than 0, there is a delta greater than 0, such that if P is a partition of AB and the mesh of this partition is less than delta, then U of Fp minus L of Fp is less than epsilon. So essentially what this is saying is that as our partitions get finer and finer, right, the subdivisions of our partition are smaller and smaller, then the upper and lower sums with respect to that partition are getting closer and closer together. And if this condition is satisfied, then the Riemann integral, of f is equal to both the lower integral and the upper integral. Right? So we know that the lower is less than or equal to the upper, and so this is saying that if f is Riemann integrable, then these two things are actually the same. Okay, so we're just going to spend the rest of the time proving this. So we're actually going to start in the opposite direction because it's shorter. So we're going to start with, if this criteria is satisfied, then f is Riemann integrable. So we know that for any given partition, the lower sum is going to be less than or equal to the lower integral, right? Because the lower integral is a supremum, it's a least upper bound, so any lower sum is less than or equal to the lower integral. This is less than or equal to the upper integral, which is an infimum for upper sums, so it must be less than or equal to the upper sum. Thus, you can say by the squeeze theorem, if you want to look at it that way, or you can write this as you can subtract the inequalities, and what you will get is that if I take the upper integral minus the lower integral, this is going to be greater than or equal to 0, right, because of this inequality here. And then it's going to be less than or equal to the difference of the upper integral minus the lower integral, which is, you can think of it as using this inequality and this inequality in tandem. Now this side here, as we take p to be finer and finer, then this side here is going to be less than epsilon. So this here is going to be less than epsilon as well, right? And so you can sort of rephrase that as this is going to 0, right? So essentially by squeeze theorem, which I can't say if we've sort of proved the squeeze theorem, but essentially, right, it's going to be bounded below by 0, and then it's bounded above by something that we can make arbitrarily smaller and smaller, and this quantity doesn't depend on our partition. So we must have, if this Darboux criterion is satisfied, then the upper and lower integrals are equal to each other. And we are going to just call this L. What we're now going to do is show that the Riemann integral of f exists and equals L. Okay? Now, we've shown previously that a lower sum is going to be less than or equal to a Riemann sum. So this is with respect to some choice of evaluation points. This is less than or equal to the upper sum. So essentially by the same idea, since the lower and upper sums are getting closer and closer to each other, we can say, how do I want to say this? You can rephrase this in a particular way. I guess you can say this here is greater than L of f p plus epsilon. So trying to find the best formal way to explain this, but you can essentially just, I'm just going to argue that, right, the Riemann sums are bounded, and since the bounds are approaching the same value, this implies that the Riemann sums are also approaching that value. And that's what it means for the Riemann integral to exist and equal some value. It means that as the partitions get finer, the Riemann sums, regardless of evaluation points, are approaching that value. So that's the first part. And I'm going to move on to the next part, or next page for space. So now we're going to show that if f is Riemann integrable, then we have what we need. So now, we're assuming f is Riemann integrable, so let L be the Riemann integral of f, and let epsilon be greater than 0, right? So we want to show that there is a delta such that we can get such that the upper and lower sums with respect to a partition with small mesh are close to each other within epsilon. So we know that there is a delta greater than 0 such that for p a partition of mesh less than delta, this implies that any Riemann sum minus the Riemann integral is less than epsilon over 4. And so you can tell right away that we're going to sort of use a triangle inequality step, where we get a bunch of pieces that are going to be epsilon over 4 and sort of add those all together. Now, it is possible to choose evaluation points such that we are arbitrarily close to the sort of the upper sum, right? So what we're going to do is say that we're choosing each evaluation point xi such that the value of f at xi is, it has to be less than or equal to m sub I, right? Because m sub I is the supremum. But we can choose such that it is greater than m sub I minus epsilon over 4 times b minus a. So b minus a is a positive quantity. So this quantity here is smaller than m sub I. But, you know, the idea is that we are choosing f such that it's pretty close to m sub I. And then, so what we have in this case is that the upper sum minus the Riemann sum with respect to this choice of partition, or of evaluation points, this is going to be equal to, right? So remember, the upper sum is exactly just m sub I times delta x sub I. So this is going to be m sub I minus f of x sub I times delta xi. And so this is going to be less than, each of these terms is going to be less than epsilon over 4 times b minus a delta xi. And now this is a constant. We can pull it out of the sum. The sum of the delta xi's is going to be b minus a. So this is equal to epsilon over 4. Okay. Similarly, there are evaluation points, which I'm going to denote by x prime, such that essentially we have the opposite idea, that we are as close to the minimums as we want, right? So this is going to be m sub I plus epsilon over 4 b minus a, and this is going to give us that 0 is less than or equal to the Riemann sum with respect to these evaluation points minus the lower sum is going to be less than epsilon over 4. Okay. It's essentially the same calculation as above, just with small m sub I. So now we apply triangle inequality. So what we have is that the upper sum minus the lower sum is less than or equal to the upper sum here minus the Riemann sum with respect to this evaluation point. Now remember, this part here is independent of, sorry. So here we're using the evaluation points that were chosen such that this quantity is less than epsilon over 4, right? And then we get the Riemann sum with respect to these same evaluation points minus the value of the Riemann integral. So here, this term is actually independent of the evaluation points that we've chosen. Right? This is going to be less than epsilon over 4, and that's because of the definition of the Riemann integral. The next term is that we're going to do L minus the Riemann sum with respect to the other evaluation points, right? And again, this term, independent of evaluation points, is less than epsilon over 4. And then the last term is that we are going to have the same Riemann sum minus the lower sum, right? And so now this is, we've chosen these evaluation points such that this term is less than epsilon over 4. So we have 4 terms, each of which are less than epsilon over 4, so their sum is less than epsilon. And that's what we wanted to prove. Okay. So this criteria, although it doesn't seem entirely useful, right, this is just an alternate way of saying that, right, if I can prove that my upper and lower sums are close together, then I know that my function is Riemann integrable, and the value of the Riemann integral is equal to the lower and upper integrals. And so what I want to do here is, this should be a quick proof, and this is really sort of the star, I think, one of the star ideas that the Darboux Criterion allows us to prove, and that is that we can now show that a continuous function, right, is Riemann integrable. And so I think this is a very key theorem because it connects sort of the topology of the real numbers to this Riemann integral, which really doesn't have anything to do with topology. And so the proof isn't that bad. So we're going to let f be continuous on AB. Okay. And we have already shown that continuity on a closed interval AB implies uniform continuity. Okay. This isn't always true, of course, because uniform continuity is a stronger condition than continuity, but on a closed interval, they're the same. So now we're going to let epsilon be greater than 0, and we are going to sort of show that we can get the upper and lower sums of f to be small, or to be close to each other. So there is delta greater than 0, such that, so now we're going to use the definition of uniform continuity. This says that whenever my x values are within delta of each other, I know that the f values are going to be within, I can really choose any positive quantity. We're going to choose epsilon over b minus a. Okay. And here, x1 and x2, I have to specify, are in the closed interval AB. Okay. So now let P be of mesh less than delta. Now since f is continuous, and we've shown that a continuous function achieves minimum and maximum values on a closed interval. Thus, f achieves m sub I and capital M sub I on every interval of our partition. Since how should I say this? Well, since the width of this interval is less than delta, this implies, right, the minimum and maximum values don't necessarily have to be on the endpoints, but whatever points, whatever values they, whatever x values they correspond to, the distance between those x values is at most this quantity, the length of the interval, which is less than delta. And so this means that the difference between the upper and lower values is less than epsilon over b minus a. Okay. So we're using the uniform continuity condition to show that the big M and little m are within epsilon over b minus a of each other. Thus, if I now take my upper sum and my lower sum and subtract them, this is going to be equal to capital M sub I minus little m sub I times delta x sub I, and this is less than epsilon over b minus a, delta xi, and then that's a constant, and so this is going to be less than epsilon. So by the Darboux Criterion, f is Riemann integrable. So again, we've used a lot of topological ideas, although uniform continuity in itself sort of requires a more metric idea as opposed to normal topological continuity. But the idea that we've used a couple results here involving the closed interval, of course that really has to do with compactness. So this is really a powerful theorem which involves a lot of the ideas that we've seen already. So that's it.